Hello friends. So in this video today we are going to solve 6th semester 2022 question paper of paper c-13 electromagnetic theory BSc 6 SEM Dibrugarh University. So this is part 2. Okay, this is part 2. So in part 1 we have already solved up to question number 2, right? Question number 1 and 2 are solved in part 1. So today we're going to solve question number 3. Question number 3, A, B, C. Okay. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. Okay. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. So here is the question 3A. Okay, we have two questions only, 3A and B. In A there is or, so 3 questions total. So state, proof Poynting theorem and related to the flow of energy at point space in electromagnetic field. What is the physical significance of Poynting vector? So now you see, I have already made a video on this topic, but there was a mistake. Let me correct that one. I will provide the link in the description box. I have written 3A, then I have given the link, but let me correct. I made a mistake there. There was when you will play the video for question number 3A, which is a link of the video is given in the description box. So after 23 minute, after 23 minute 27 second, you will get this step, the integration, volume integration del E cross H d tau minus mu naught volume integration half partial derivative of AC square with respect to t, then again volume integration E dot J d tau epsilon naught volume integration of half then again partial derivative of E square with respect to t. So that's what you will get. Then what I have done, I have taken this del t, I have taken this one as common. Okay, I have written outside. So as soon as you write this outside the bracket, here you see from these two terms, this one and this one, in both we have volume integration, we have differential coefficient as well, that is taken outside, right? Then this term within the bracket, here again I have written del t. That should not be written actually. It's supposed to be mu naught AC square plus epsilon naught E square. That should be the term. Okay. So you have to change here also within the bracket. Once you have written this del t outside the bracket, once you have taken common, then here you should not write this. Okay, I made this that mistake, and I have mentioned in the thumbnail of that video also. So if you watch that video, so when you will get this step, after this step you continue. When you continue, just change the term in the bracket. Okay, so hope you have got my point. So here it should be again E square. That's how you have to change this here also. Then again here you see this is question number equation number 7 you will get in that video. So here also this term should be only AC square. So that means you should write mu naught AC square plus epsilon naught E square within the bracket. Okay, so change everywhere here also. Okay, mu naught AC square plus epsilon naught E square. That's how you need to change. Okay, so now you see there are two questions, this one or this one. So now let me show you this one. Okay, answer of this question, you get this, you will get this in the video. Okay, just click the link given in the description box. Okay, now let me solve this question. Okay, so that for an electromagnetic field, the energy density is given by this expression. Okay, let me show you how to solve this. Question number 3a, or okay, so energy density in electric field, electromagnetic field. Okay, so here we're gonna find the energy density one by one in electric field and magnetic field. Okay, first let us find the energy density in electric field first. Okay, energy density in electric field. Okay, energy density in electric field. Okay, so now you see, first let us find this. So first let us consider we have a parallel plate capacitor. Suppose these are the two plates, one plate is positively charged. Okay, so we have plus q charge here we have minus q charges, okay, on this plate, and area of each plate is suppose A. Okay, and so let me write what I have considered here. Now you see, electric field due to a positively charged plate, that will be given by, now you see, hope you know this, that the electric field due to a thin sheet, okay, charged thin sheet, is given by sigma by 2 epsilon naught, where sigma is charge density, that is q by A, right, surface charge density. So hope you have you know these things. Okay, so that's why electric field due to one plate only this positively charged plate is given by, let me write E positive, that will be given by sigma 2 epsilon naught, and sigma is surface charge density, so we can write q by A, that means charge per unit area, right? So where sigma is equal to q by A. So magnitude of charge in both plate is same, but one is positively charged, another is negatively charged, and magnitude of charge is q, right? So electric field due to both plate will be electric field due to both the plates, that will be 2 times of this, that will be given by E is equal to, if you 2 times this, then you're gonna get q by A epsilon naught, right? So now you see, let me take this as equation number 1. Now you see, what will be the force on this negatively charged plate q, negatively charged plate due to this positively charged plate, right? So here you see this plate is negatively charged, and the force experienced by this plate due to the electric field of this positively charged plate will be, so let me write here, magnitude of the force on negatively charged plate due to the positively charged plate due to the positively charged plate is F is equal to, now you see, electric field due to the positively charged plate, that is E positive, into charge on the negatively charged plate, that is Q. So as we are taking the magnitude only, so I am not writing this minus sign. Okay, so hope you have understood this. So this is the force. So we have already got that E positive is equal to this one, so let's put that here. Then if you put, instead of E positive, if you put this, then Q into this Q, that's gonna be Q square, then you're gonna get this expression Q square by 2A epsilon naught. That's what you're gonna have, right? Let me copy this and let me take a new slide. Okay, now you see work done to displace the negatively charged plate. Let me copy this diagram again. Okay, so here you see, this is the parallel plate capacitor, right? So now you see, if you want to suppose displace this plate through a distance, suppose x, if you want to displace this negatively charged plate through a distance, suppose x, okay, then you need to do work, right? So work done to displace the negatively charged, don't write this way, write the word completely, negatively charged plate through a distance x against this force, F, okay, is given by W is equal to F into X, force into displacement, right? Now the energy of electric field in this volume means this volume. So you have shifted this plate to through this distance x. Now the area of this plate is A, then volume of this will be A into x. So now, I have drawn this one in the two-dimensional space, so it's supposed to be like this, the plate should be like this, right? If you have displaced this plate through this distance x, then volume of this portion will be A into x. A is the area of this plate and this is x, so A into x gives the volume, right? Hope you have understood this. Okay, so the energy of electric field will be stored, this work done will be stored as the energy of this electric field in this volume, right? Hope you have understood this. So now the energy of the electric field in the volume x into A is, so let me write here capital U, okay, so this is, let me write here E, okay, to represent energy. So F, we know that is this one, Q square by 2 epsilon naught, A should be there, I forgot to put the A, into X, that's what you're gonna get. So to find the energy density, you need to divide this energy by volume, right? By volume. Therefore energy density is, let me write down small u, E, okay, so capital U, E divided by the volume is x into A. If you divide this quantity by x into A, then what you're gonna get, so here x will be cancelled, right? So you're gonna get half. So let me write this one first. Q square then 2a square, sorry, so there is already, I have already written 2 here, so a square epsilon naught, that's what you're gonna get. So if you multiply here one more epsilon naught, then this is supposed to be epsilon naught square, so that's why you can write this part here. You see, you can write this way, small ue, that is energy density, half epsilon naught. You can write this is nothing but electric field intensity E that we have got in equation number 1, this one, right? So from 1 or using 1, right? Hope you have understood this. So this is the energy density for electric field. Now similarly let us find the energy density for magnetic field as well. So let me take a new slide. Now let us consider a solenoid. Okay, solenoid of radius r, its radius is r. This is the solenoid, right? Its radius is r, its radius is r, and length is suppose L, and number of turns is suppose n. There are n number of turns, right? N number of turns per unit length. Okay, turns, number of turns per unit length, right? This is small n, and the current through this coil is suppose I. Okay, so let me write what I have considered. So now here you see the magnetic field in this solenoid. Magnetic field in the solenoid that will be given by H is equal to Ni, or you can write in terms of B also, B by mu naught Ni, that means B is equal to mu naught Ni. Now you see, as we need this result here, we need in terms of H, so that's why we're going to use this relation instead of this. Okay, so if you need to prove this, suppose energy is equal to half epsilon naught E square plus B by mu naught, B square by mu naught, right? If you need to prove this one, then we're going to use this relation. And if you need to prove this one, instead of this you can prove this one also. So if you need to prove this, then we're going to use this relation. That's as simple as that. Okay, so now you see, sometimes this may be asked. Okay, so here you see, instead of this relation may be given in this way: u is equal to half 1 by 2 u is equal to 1 by 2 epsilon naught E square plus mu naught. Instead of mu naught H square, it may be given B square by mu naught as well. Okay, it's very simple. Once you have proved this, you can write that instead of H you can write B by mu naught, right? Okay, because you see mu naught H square, if you replace the H square by half epsilon naught E square, if you replace the H square by B square by mu naught square, then you're gonna get half epsilon naught, E square plus mu naught B square. This mu naught cancels mu square, so here you're gonna get mu naught. Okay, so hope you have understood this. So now here you see, and self-inductance L, that is given by mu naught N square pi R square L square. Okay, self inductance is given by this, and magnetic energy is stored in a inductor. Okay, so this solenoid is nothing but an inductor, right? Magnetic energy is stored in the inductor. That is given by, let me write U capital B, okay, is half Li square. Okay, so instead of L we're gonna write this expression, that is mu naught n square pi r square L square, right? Now you see volume inside this solenoid will be given by this area of this cross section into its length, right? This one is the volume. Actually it's sorry, L square, and there's supposed to be a I forgot to write this, sorry. Okay, I square, and this should not be L square, this is supposed to be only L, right? This should be L only, not L square. Sorry, I made the mistake. And now here you see this is nothing but volume. Pi r square into L is nothing but the volume, right? So here we're going to write that half mu naught n square I into I square into volume, that is V is equal to pi r square L, volume enclosed by the solenoid, volume enclosed by the solenoid, right? Volume enclosed by the solenoid. Now you see energy density. To find the energy density you have to divide this by volume, right? Then what you're gonna get? Then energy density let me write a small ub, which will be given by capital U B divided by the volume V, right? So capital UB we have got half mu naught n square I square V, half mu naught n square I square V divided by volume V cancels, and then what we're gonna have here, you see 1 by 2, right? Mu naught, so ni square can be replaced by h square. From this equation you can see by h square. Let me take this as equation number 2, and let me use here equation number 2 using equation number 2. Okay, so this is the energy density in magnetic field, right? And we have got the energy density in electric field as well. So adding these two, we're gonna get energy density for electromagnetic field U is equal to, by adding energy density for electric field plus energy density for magnetic field. So energy density for electric field is half epsilon naught E square, that is what we have got, and for magnetic field we have got half mu naught H square, right? So half can be taken common, then epsilon naught E square plus mu naught H square. That's what we can prove. So hope you have understood this. So now let's move on to next question. Pause the video and note this. Next question is write Maxwell's equations. So let me clear this first. Okay, sorry. Okay. Next question. Write Maxwell's equations in differential form and discuss the physical significance. So let me give you write the answer. Question number 3B. So differential forms of Maxwell's equation. Okay, Maxwell's equations in differential form are, you can write, divergence E is equal to rho by epsilon naught, or you can write this way also using symbol divergence E, like this also. Okay, so that's how you can write. Then divergence B is 0. Then curl, that is del cross E, also you can write curl of E, that is minus del B by del T, and curl of B you can write in terms of H as well, J plus epsilon naught del E by del T. So these are the four Maxwell's equations. This is equation number 1, this is equation number 2, this is 3, and this is 4. So now let me explain these equations one by one. So equation number 1, so what is equation number 1? This is nothing but Gauss law. Okay, so the equation number 1 is Gauss law. For electricity. Sorry. That states, or who is states that electric flux through a closed surface is equal to the 1 by epsilon naught times the total charge enclosed by the surface, right? Actually what happens when you write this equation in integral form, we get this, right? Integration E dot ds q by epsilon naught. Q is the charge enclosed, and this represents electric flux. So if you write this in differential form, instead of charge we used to write charge density, right? Hope you have understood this. So this is the statement of Gauss law in electrostatics, right? So equation number 2, this equation number 2 is the Gauss law for magnetism. So let me write here electrostatics, right? Okay, so equation number 2 is Gauss law for magnetism. Okay, so that is magnetic flux through a closed surface is 0. Okay, that is given by this equation number 2, right? And the third equation, equation number 3, let me take a new slide. Okay, equation number 3 is Faraday's law of electromagnetic induction, magnetic induction, right? Signifying that changing electric field and changing electric field, sorry, not changing electric field, I have to write an electric field is produced by a changing magnetic field, by a changing magnetic field, right? So now let's come to here. You see the fourth one is Ampere's law, but it was modified by Maxwell. He replaced the term J by J plus epsilon naught E by del E by del T. So original Maxwell equation was this, Ampere's law was this, curl B is equal to mu naught J. So he replaced this term by this, okay? So where this epsilon naught del E by del T represents the displacement current density, right? So hope you have understood this. So in the next video we're gonna solve the remaining questions. Okay, thank you for watching. See you in the next video. Bye bye.